All right, so let's take a look at today's lesson. The last time we worked with vectors with like the geometric representation. We drew them, we added them by drawing them head to tail, that kind of thing. We drew the resultant vector. What we're going to focus on this time is the algebraic representation of a vector. We're going to look at the components and all that kind of fun stuff. So let's take a look. So if our vector is in standard position, our initial point is going to be at the origin. Okay, it's going to be at the origin, like this right here. This vector is in standard position. It's drawn, it begins at the origin, and then it proceeds onward. The components of the vector, and that's crazy math talk, so let me just explain. The components of the vector are talking about if we were to make this a right triangle, this section of the right triangle would be the x component of your vector, and this section right here would be the y component of your vector. That's what it means by components, x and y components. If we're in standard form, what we can actually do, this component form, this is called component form. This is the component form, and those things right there are called chevrons. And so that's writing our vector in component form. And if we have the component form, which we do here, to draw the vector, what we would do is we would simply go out to the point 7, 4, which is right here, and then we would draw the vector from the origin and we would connect it to 7, 4. That's how we could draw a vector, by using its component form. Okay, so I'm going to pause here for just a second. So does everybody see how we get our x component and our y component? The x component is the distance along the x-axis, and the y component is the height or the distance along the y-axis. That's what the components are. This little formula, displacement equals final position minus initial position, this formula, what it's going to do for us is it's going to help us, like let's say we have two different points. Let's say we have the point 1, 2 and the point, I don't know, 5, 7. And we wanted to draw a vector that was between those 2 points. This is the formula that would allow us to do that, and that's like our number 1 on the examples we're getting ready to do. So we will be able to actually write the component form of the vector that would like start at 1, 2 and would head to and end at the point 5, 7. So that's the kind of thing we're going to learn how to do, and we would use this formula. We would take the final position, which is the final point, minus the beginning position or initial position, which is the beginning point. And we're going to look at that in a moment. Okay, that's what that formula is for. So we can do something called, we talked about magnitude last time. So magnitude is the length of the vector. So let's take, just for instance, let's take this vector that we have written up here. Let's just look at, I'm going to pull this out, this vector. Well, this is 4 spaces, this is 7 spaces. The magnitude is simply just realistically, it's just the hypotenuse of the triangle. It's the length of the hypotenuse of the triangle. That's all the magnitude is. That's all this fancy formula means. It's simply the length of the hypotenuse. So if I wanted to find the magnitude of this vector, the vector 7, 4, I would just do, we can call this, I don't know, let's call it C. We would say c squared equals 4 squared plus 7 squared. So c would be the square root of 4 squared plus 7 squared. And that's this exact formula right here. It's simply just finding the hypotenuse of the triangle. That's what the magnitude is. So it's going to find the length of the vector. Okay, so as we're looking at this formula, we take the x component and square it, and the y component and square it, and square root it. So it's virtually just finding the hypotenuse of the triangle. Okay, is everybody okay so far? Yes? Okay. So what we can do when we have the component form, so let's look at our vectors down here. So we've got vector u has an x component of A and a y component of B, A1 and B1, and vector v has an x component of A2 and a y component of B2. That's just kind of setting the stage for us. If we want to add the vectors, we don't actually have to draw them out and add them, you know, like we did last time. We can actually simply add them algebraically. What would you do? Well, you would take the x components, that, you know, these x components, and you would add them together, and that would become your new x component, or the resultant x component. And then you would take your y components, which are here, and you would add them, and they would become your new y component, or your resultant y component. So we don't have to do it by hand like we did last time, where we drew the vectors and then we drew the resultant and did that. There's another way to do it. It's an algebraic way. And we can subtract vectors as well. And it's the same concept. We would pair their x components and subtract them. We'd pair their y components and subtract them, and that would give us the new vector. So this is our algebraic operations on vectors, and we would need them to be in component or IJ form. Okay, any questions on that so far? So let's talk about vectors in terms of I and j. Okay, so these are, I and j are really kind of little big deals. And they're so if you're writing the vector, it's like I hat and j hat. They're the only vectors with hats, and they are so excited about it. I'm just saying, they're like special, and don't forget to give them their little hat or they will be very upset. And I think all the other vectors are jealous and they want hats too, but only I, j, and k have hats. K would be in 3 dimensions. So what is I and j? Here's the picture right down here of I and j. I and j are unit vectors. Okay, the unit vector. And a unit vector, do we remember, I'm just going to throw this out here, do we remember what the specific criteria to be a unit is?
Radius of 1.
Radius of 1, yeah, it's a 1, right? The unit vector has a length of 1. The length is 1 for our unit vectors. Now these are special unit vectors because I is on the x-axis at 1 unit, and j is on the y-axis at 1 unit. They're not just anywhere. I can draw a unit vector, really just a plain old unit vector, anywhere I want. Like I could put a unit vector here. Maybe that's a unit vector, and that has a length or magnitude of 1. But I and j are special in that they correspond to the x and the y-axis. That's what makes them special, and I think that's why they get a hat. And when professors write them, they'll say I hat and j hat. It's like, wow, that's even in their name. Okay, it's kind of cool as vectors go. So that's the deal with I and j. Now what we can do is we can go back and forth. So recall the vector that we had up here. This vector is in component form, right, with the chevrons, the 7, 4. Well, you can write that exact same vector in a different form called, this is the I and j form. So right over here, it's the same vector, just written in a different form. Okay, so that's just a different way to write them. But they mean the same thing. We can take any vector and we can create it. We can cause it to be a unit vector. We can take any vector and make it into a unit vector. what we would do is something called, the vocabulary word is normalizing. Normalizing means that you're making a vector into a unit vector. You're making it however long it is, it doesn't matter. You're going to force it to have a length of 1. And there are a lot of benefits to forcing a vector to be the length of 1, which you would learn in follow-on courses. We're just going to learn how to make the vector a unit length of 1. What we do is we use this formula right here. This formula will normalize any vector for us. So what we do is we take the vector and we divide it by the magnitude of the vector. So these double bars are one way to write magnitude. Some textbooks also use a single bar. Oops, I think the single bar is a little confusing because some students might think that means absolute value when they really are meaning magnitude. That's why we're going to use the double bars. I don't recall what your textbook does, whether it's a double bar or a single bar, but it's just talking about length, the magnitude. So we can create a vector or cause a vector to be a unit vector by simply dividing the vector by its magnitude. And we're going to practice that as well. The last concept we're really not going to use very much at all. We won't, but it is an important concept that I just wanted to talk about. It's called the equilibrium vector. So you probably have seen like old-timey scales, you know, so and I'm a terrible artist. I'm going to apologize right now. You know, where there's like a tray on one side and a tray on the other, and you can put like stuff in each of the trays and it'll balance or not. You know how it swings back and forth and it balances? So an equilibrium vector, what it does is it balances out. It causes the original vector to turn to 0, to make its effect turn to 0. So the equilibrium vector of a resultant a plus b would actually be the opposite of the resultant a plus b. That would be the equilibrium vector. It just would undo whatever the original vector did and cause the net result to be 0. Okay, so that's just a concept that we're talking about. We're really not going to, and the concept might show up in a word problem or something, but I just want us to understand what it means by an equilibrium vector. And how would we find it? We would just take the opposite of whatever vector we are working with to get its equilibrium. Okay, how are we doing so far? Everybody okay? Okay, so we have just a few examples to work through. So let's start. Our first example is giving us 2 points and asking us to find the vector between the 2 points in component form. So what I would like to do, just to make sure we understand conceptually what we're doing, is I want to graph these 2 points. Probably need to move that over. So let's see, we've got -1, 3. So that's where P is. And then we have -6. -1 should be like down here, and that's Q. And our vector is starting at P. Its initial point is P, and its terminal point is Q. So what they're asking us to do is they're asking us to write that vector in component form. And component form is the chevrons, the little chevron things. That's component form. It's what it's asking us to do. And this is where we're going to use our formula that I showed you on the first place, that displacement formula. So we need to note where our beginning and ending is. So this is the end point, and this is the beginning point, because if I get them mixed up, I'm going to come out with the wrong vector. Okay, so what do? We're going to do, so PQ, vector PQ is going to be I take my end x value, which is -6, and I subtract my beginning x value, which is a -1. That's going to be my x component. Then I take my end y value, which is a -1, and subtract my beginning y value, which is a 3. So that is going to give me my vector in component form. So -6 minus -1 is -5. -1 minus 3 is -4. So this is what they asked us for. That's in component form. And I want to show you, I'm going to draw PQ in standard form. So I want you to get a feel for what this actually means. So if I draw PQ in standard form, I would start it at the origin. Then I'd go over 5, 1, 2, 3, 4, 5, and down 4, 1, 2, 3, 4. So I'd be like right here. And I draw my vector. And we can see that it's the exact same vector. It's just oriented at the origin. It begins at the origin. So what we did is we took this vector that was just out in space somewhere, out in our Cartesian coordinate system somewhere, and we wrote it so that if we graphed it, it would be in standard form. Does that make sense? Is everybody okay that what I did was I simply found the components of the vector, and if I wanted to graph it, it would look exactly like the vector that we're mirroring. Okay, so that's the component form. If I wanted to write that in ij form, we would say PQ equals -5i hat. Oh, he gets his little hat. He's so excited. Okay, minus 4j hat. So this would be writing it in ij form. They mean the same thing. They're just a different way to write a vector. You'll see both types. Okay. How are we doing? Okay. So, let's see. And lastly, so we found the component form. The last thing they want us to do is find the magnitude. Okay. So that's a formula. If we wanted to think about it, I could, have my little formula. So it's what we've got 5 this way and 4 this way. And so it's actually just Pythagorean theorem, our magnitudes. The magnitude of PQ would be square root of -5 squared plus -4 squared. It's just going to give us our length of the vector. And that is actually the square root of 41. So our magnitude is the square root of 41. Okay, so we've just practiced writing a vector from 2 points, and we've practiced finding the magnitude of a vector. Any questions? Okay. So let's take a look at number 2. So number 2, we're asked to draw a diagram that shows the resolution of the vector into its rectangular components. Now I know that's a lot of math words. They're just asking you to draw the vector and find the x and y components. That's what they're asking you to do. Rectangular components just means, like this. They want us to write it like that. The x and the y. Okay. So bearing, 3/4 is a magnitude. It's a magnitude. And bearing is the direction of the vector, but this is the direction in like compass form. A bearing is like a compass. So we're going to calculate it or look at it differently than we would if it was just a regular old direction. And number 3 is a regular old direction. So I put these next to each other so that we could compare and contrast. So we're going to draw our axis. All right, so if we're in bearing form, it's like compass. We're going to start, this is like the north line, we're going to start on the y-axis and we're going to rotate 255 degrees. So that takes us 90 degrees, that takes us 180 degrees. This takes us probably around 255. So we know we can't go all the way to that line because that's 270. So this is 255 degrees. We notice how we measured from the y-axis, which is like the north line, and we went clockwise. So compass form is from north clockwise. From north clockwise. That's like the compass directions. Bearings, they use the word bearing or compass. That tells you that we go from the north line and we go clockwise. Okay, so if we want our x and y components, what we're going to do is we're going to basically drop a line to our x-axis. We're going to consider this as a right triangle, and we're going to find this side of the right triangle, which is x, and this side, which is y. Yes, there are formulas for it, but I really want you to think about it in terms of just a right triangle. We don't need to memorize any other formulas. We already know how to work with right triangles. We need this. I'm going to put just we need this angle measure. We can find that, right? Isn't that a fairly easy thing to find? Wouldn't we do 270 degrees minus 255? Won't that give us that little angle measure right there? Yes, 270 minus 255. That gives us, so this angle measure is 15 degrees. So I have a right triangle, and that measurement, angle measurement of the right triangle is 15 degrees. My magnitude or length of my vector is 3/4. So I've got the hypotenuse. Okay, so let's think about our right triangle trig stuff. If I've got the hypotenuse and I want the adjacent side, I would use which trig function? Cosine. I would use cosine. So we're going to do cosine, and you would have a calculator for this. Cosine of 15 degrees equals adjacent, which is x, over hypotenuse, which is 3/4. So I use my calculator, and I get that my x coordinate or x component is 0.7244. So I'm going to hold on that for a second. Now I'm going to find the y component. So I need opposites, and I have hypotenuse, so that should scream sine to us, right? Sine of 15 degrees equals opposite, which is y, over hypotenuse, which is 3/4. So y is going to be, let's see, 0.19411. 19411. Now here's the issue. I'm just going to give you a warning. Our calculator, when we do our calculator, it's not going to give us the correct signs of x and y. It's just not. And some students don't pay any attention and they just write what's on the calculator. That's a little bit of a problem because what is my what is the sign of my x component? It's negative. And what is the sign of my y component? It's negative, right? We're in the third quadrant. So when I write it, because they wanted us to write it in component form, we'll just call this vector v. So I'll open up my chevron. It's actually going to be negative 0.724, comma, negative 0.194. That's that vector in component form. Oh, isn't that nice? Come back. Okay, there we go. Okay, so that's the vector in component form. Please pay attention to where it is. Yes, ma'am.
Sorry, I have a question about like the 270 degrees part. Can you just like go over how you got that? I get like the
Sure. Sure. As we're headed this way, this part, that much is 90 degrees, right? And then that much is 90 degrees. And then this part is 90 degrees. So all the way, those three sections would give us a total of 270 degrees. So if I go all the way to here, I have 270 degrees, but I don't want to go that far. I want to go just to here. So I would do 270 minus 255. Is that okay? Okay. So those are components. Are we okay with that? Now, the magnitude of the horizontal and vertical components, that is a weird question, because what does magnitude mean? We need to understand the words. What is magnitude? It's a size, right? It's a length. Well, we know what the x length is, right? We found it already. So they're asking us a question a little bit weird, but we can handle it. I mean, it's just a length. So horizontal, the horizontal magnitude would be the, 0.7244, and it's a length. So we're going to make it positive and put units on it, because the units are inches per minute. So that's the only kind of weird thing. And the vertical is going to be the y, which is 0.1941 inches per minute. And we're making it positive because they're asking about magnitude. And the hypotenuse of a triangle is always what? Always positive. The magnitude is positive. It's going to be positive. It's a positive distance. So we had to actually make a little bit of adjustment in our thinking. Is that okay? Okay. The last one, I intentionally did a regular one because we did the direction and compass form. On the last one, we're wanting to do just regular old direction. Regular old direction. And regular old direction, which is out of context, so no context, we go from the we go from x-axis counterclockwise. So if they don't tell us it's a compass or north, south, east, west, then it's regular old direction, which is from the x-axis counterclockwise. Okay, so let's do this. So this vector, if we want it in component form, which I know a lot of students prefer, think it's easier to work with if it's in component form. So I wrote it in component form for you, though our final answer needs to be back in IJ form. Okay, let's just work with it this way. So let's draw a picture. So I am 4 spaces this way and 4 spaces down. So we're writing it in standard form. There's my vector. We want the direction angle. They're calling the direction angle. This is the Greek letter alpha. Right here, that's the Greek letter alpha. So we're starting at the x-axis and we're going counterclockwise to the vector, and that is going to be alpha. That angle measure is going to be alpha. That's a regular old direction, no compasses. Notice the vast difference in the way that I'm drawing both of those. If you look at number 2, see how that angle measure was drawn out, starting at the north, going clockwise. But number 3, it's a regular old direction. We're starting at the x-axis and we're going counterclockwise. Okay. So they're wanting us to find that angle alpha. Let's go ahead and let's say that this is theta. And I'm going to think about it like a triangle. I would highly encourage you to just think about these as right triangles. It will make your life easier. This length of this triangle is 4, and this length is 4. It's actually -4. So I want that angle measure, and I have opposite and adjacent. Which trig function could I use to find that angle theta? Tangent. I want to use tangent. So you see how a lot of these lessons pull from your previous knowledge? So we're going to do tangent of theta equals opposite, which is -4, over adjacent, which is 4. So our calculator is going to do this for us. We will have a calculator for this lesson. So what we're looking at is arctangent of -4 over 4. Our calculator only knows how to give function values, which are called principal values. It does not know how to do relation values. So when you put this in your calculator, your answer is going to be -45 degrees. That's what it's going to be. That's the function value. So in reality, in our little triangle, what is theta? Theta is just 45 degrees. Right? That's all it is. And if I want to find alpha, how am I going to find alpha?
360.
Absolutely, 360 minus. I'm going to do 360 degrees minus 45 degrees. And that's going to give me, what, 315? So alpha is 315 degrees. That's our direction angle. Okay, the last thing they want us to do is they want us to turn it into a unit vector. We're going to normalize it. So we're going to turn it into a unit vector. Okay, we can do that. So what do we need to find? We need to find the magnitude. We need to find the magnitude of V. It's going to be the square root of 4 squared plus -4 squared, which is square root of 32, which simplifies to 4 root 2. That's our magnitude of the vector V. Okay, so our magnitude is 4 root 2. So to get our unit vector, so what are we doing? We're taking this particular vector and we're shrinking it to be 1 unit long. That's what we're doing. So when we do that, we're shrinking it. It's actually going to look like, like this. It's going to be like 1 unit long. It's going to be little bitty, but it's going to go in the exact direction of the vector, and that might not show up very well. Let's try with a different color. So we're overlaying a little baby vector. We're finding the components of the little 1 unit vector that's going in the exact same direction as the original vector. They just shrunk it. Okay, we're just going to shrink it. All right, so to do that, we're going to call it u, because unit vectors, they usually call them u. The unit vector is going to be basically 4 over 4 root 2 and negative 4 over 4 root 2. Now, they gave us the original vector in ij form, so our answer needs to be back in the form they want. So let's do that. It's not a problem. So our unit vector is going to be, let's reduce, so we get 1 over root 2i minus 1 over root 2j. And there's our unit vector. So that represents that little tiny vector that I wrote in pink on top of the original vector. Okay? How we doing?